It's a great pleasure to have Adam Zsolt Wagner speak today on reinforcement learning and pattern finding. You're welcome to interrupt him anytime by unmuting yourself, but otherwise, please stay muted. Thank you.
Yeah, thank you so much for all of you for coming and for having me. I want to tell you about two different ways you can use machine learning that is sometimes a little bit helpful in research in mathematics. And I will talk about reinforcement learning in the first half, and then in the second half, I will talk about the recent experiments using some generative methods. And everything in the second half will be joint work with Jordan Ellenberg from Wisconsin Madison, from Marijn Heule, who is at Carnegie Mellon, and with Geordie Williamson, who is in Sydney. But let me get started with reinforcement learning. So in some way, this is the simplest possible thing you can try when you want to use machine learning in mathematics. The main idea is as follows. There are these companies, such as DeepMind, for example, that have created these programs that can play chess, Go, Atari games at really superhuman levels. And the interesting thing about these programs is that they started from knowing absolutely nothing about the games, and they figured out everything just by playing the games many, many times just by themselves. So given how successful these self-learning algorithms, these so-called reinforcement learning algorithms were, how nice would it be if we could find a way to use them in mathematics as well? And you can imagine how this could be possible. Instead of inputting the rules of chess, why not input the rules of a game where the goal of the player is to construct a graph with as many edges as possible without constructing any cycles of length 4. So the idea is to take any kind of conjecture or problem in mathematics, encode it as a game, and try to use these self-learning algorithms to get good at this game. And in this particular case, how would you phrase this problem as a game? Well, there are a couple ways to do it. Simplest thing would be to start offering each edge one by one to a player, and for each edge, the player can decide, do I want this edge or do I want to reject this edge? The game goes on until the player has made a decision for each possible edge, at which point the game ends, and we give the player some kind of final score that represents how well they did in this game. And for this particular example, the score could be like, you get 1 point for each edge you included, and you get, let's say, a 100-point penalty for every single 4 cycle you created. The idea is you take a problem in mathematics, you encode it as a game, you throw a reinforcement learning algorithm at it, and when you come back from a holiday a few days later, you'll find a program that's very good at constructing graphs with many edges and no 4 cycles. The good thing about this approach is that if this works, and that's a big if, then this would be a very, very general approach. You could take almost any mathematical problem that could be phrased as a game and that could potentially have, let's say, a conjecture that could potentially have a finite counterexample. You could input it to a reinforcement learning algorithm as a game and tell it to try to get good at the game of finding a counterexample to the conjecture. That's what we're going to try to do here today, and we'll see how well this actually works in practice. So our goal will be to find counterexamples, open conjectures with this self-learning method. But this is still very, very vague, so let's be more precise with what experiment we are going to look at here right now is. And in this particular experiment, I will do everything by avoiding to input any human insight as much as reasonably possible. Sometimes it's not clear how you could really avoid any human insight, but let's at least make an effort to do that. Now, if you decide to do this, this decision has some consequences. Namely, you won't be allowed to, for example, change the setup or the neural network in between different applications. So what we're going to be after in this particular experiment is one general purpose setup, a black box, simple learning algorithm that is maybe not as good as it could be, but it's something that you can simply throw out 100 conjectures and see what happens. That's what we're going to try and see what happens. And let's immediately jump into one baby example from the literature. So this is a conjecture from literature. It's not true. It's been refuted in 2010. But let's see how we'll go about applying our method to this conjecture. So this conjecture says that from any graph, take the largest eigenvalue and the matching number, and the sum of these two is at least some function of the number of vertices. For this talk here, let's forget everything we know about eigenvalues and matching numbers, and let's focus only on how would we go about attacking this conjecture in principle if we didn't know anything about mathematics, We only wanted to use reinforcement learning. Well, we need to do two things. We need to decide how to phrase this conjecture as a game, and we need to decide what the reward function should be. Phrasing it as a game can be done several different ways. One simple way would be offer edge one by one, and to construct a graph like this. So for each edge, the player can accept the edge or reject it. At the end of the game, after n choose two turns, the player ends up with some kind of graph. And what should the score be in this game? Well, we want to minimize lambda 1 plus mu, so the score can be simply lambda 1 plus mu of the final construction. In this case, we want to minimize it, but that's the same as maximizing minus lambda minus mu. And that's, in the baseline, that's really all we have to do. Decide what the game is, what the reward function should be. Now you can throw it at the reinforcement learning algorithm for a fixed value of n, that's the n equals 19. And when we come back from holiday, a couple of days later, this is the picture we'll find. So here, the blue line represents the score that the program was able to achieve. In the very beginning, it had no idea what it was doing. It was just generating random graphs. Then quickly, this blue line starts decreasing, then it stagnates a bit. But eventually, after some number of steps, this blue line went below this orange dotted line. And the orange dotted line represents the right-hand side of this inequality. So the fact that eventually blue went below orange simply means that at this point, the program found a counterexample to the conjecture.
If this it can only refute specific n. It cannot refute conjectures for sufficiently large n, right?
That's a very good question. Yeah. So I don't know of a good way to make this method work for multiple n's. There are some things that I could imagine you could do, but we tried them and it didn't really work very well. So for now, we decided to just stick with one particular n at a time.
So that's exciting. How long did it take? How long was your holiday?
Well, this is a very, very simple example where there's a counterexample of 19 vertices. So if you choose the parameters correctly, you can do it in a matter of seconds or minutes. If you choose the parameters wrong, then it will take you a couple of days. There's a fair amount of luck involved as well. So different runs can have different results. But basically, whatever you try on this one, you will, within a couple of days, find a counterexample with this method.
That's a beautiful example. Thank you.
And here, Adam, I guess you just tried consecutive values of n, right? From small.
Oh yeah, absolutely.
You didn't fix 20 at the beginning. You just
I tried a bunch of different values. I tried 15, I tried 30. I saw that for 30 there is a counterexample, and then I just found, I think 19 is actually the smallest possible n for which this conjecture is false. And this is the counterexample for 19. I'm pretty sure that this conjecture is true up to 17 or 18. And it just happens to be false for 19. And what else you can do is you can see at how the best constructions have evolved over time. You can see in the beginning, it has no idea what it's doing. It's just generating random nonsense. Quickly, it realizes the sparse graphs are the way to go. And eventually, this kind of balanced double star structure has emerged. Now, in this example...
Another question. If we do it by completely brute force for this particular example, 2 to the power 19 choose 2 is not such a big number. It's feasible.
2 to the power of 19 choose 2, that's 2 to the 200. That's way too large.
So that's not feasible even on a supercomputer by fully brute force?
Yeah, you cannot do this fully by brute force. So you cannot check 2 to the 200 different graphs. But for this particular example, you can definitely find a counterexample with other algorithms as well.
Yeah.
So this is small enough. It's just an illustrative example to start out with. And what I want to say about this example is that here we had a conjecture. There is an obvious way to choose a reward function, obvious choice of score, and obvious ways to phrase it as a game. We plugged it in, it worked. This is a dream scenario. If this happens, there's really nothing to talk about. We tried the method, worked, end of story. Unfortunately, maybe fortunately, in practice, that's almost never happens. So what I want to do here is show you a couple other examples, and I chose these other examples in such a way that each of them will illustrate some different aspect of this method or different things that could go wrong and what one can do to fix, to make the method work in those cases as well. So I just want to highlight several different aspects of what can happen if you use this method in practice. And let's immediately jump to the second conjecture, which is going to be very, very similar to the previous one, but something different will happen if you try to use the same method. So here in this conjecture, it says that from any graph, phi, the proximity plus delta, some distance eigenvalue is always positive. Once again, let's completely ignore what proximity and distance eigenvalues are. Let's focus only on how we will disprove this conjecture using only reinforcement learning. Well, we can just do the same exact thing. We can phrase it as a game by offering edges one by one. And the reward function previously was lambda 1 plus delta, lambda 1 plus mu. Now, all we have to do is change lambda 1 plus mu to pi plus delta. And otherwise, we can use the same exact program we had before. If you run it for, let's say, n equals 30, and once again, you take another holiday, you will come back to a picture like this. This is the best construction where the program was able to find after a couple of days learning. Value of pi plus delta for this particular graph is something like 0.4. But the conjecture was that pi plus delta is always positive. So this graph is not a counterexample to the conjecture. This is an example where we tried reinforcement learning on a problem. It found pretty good construction. It was not able to find a counterexample to the conjecture, but this is by far the most common thing that happens. But many times, even when reinforcement learning fails, it still can give us helpful information so that the human can take over and finish the job. Because if you take this graph and you put it in a tray and you take it to any undergraduate mathematician, it will be completely obvious to them what type of graphs they should try if they are hoping to find a counterexample, right? Because you just take this flower, you just increase the number of petals, you make these two sticks a bit longer, a bit shorter. It turns out if you start playing around with things like this, there's no way that you will not eventually stumble upon a counterexample if you try hard enough, because already something like this happens to be a counterexample of the conjecture, as long as you have enough leaves at that point, at least 190, turns out. So this was just to illustrate that many times reinforcement learning completely fails. It doesn't manage to find a counterexample. There might not be any counterexample for n less than 100, who knows? But many times it can still give us enough insight to help as mathematicians make progress in the problem.
In hindsight, once you suspect this very, very special form, do you think you could have gotten it much faster? And
Absolutely.
Is there a conceptual reason why this is a reasonable thing, or is that came out?
I have absolutely no intuition about this conjecture. I don't remember where it came from. I would guess after I see a picture like this, I will definitely try sparse graphs in some way, maybe trees. And of course, once you decide that you will search for only trees, then it's possible to find constructions like this. Yeah. In this experiment, I was really trying to avoid me doing any kind of mathematics, and I really just wanted the computer to do as much as it can. But I agree, in real life, you should always input as much intuition or human knowledge as you can. It's definitely not the case that computers can just take over and do everything. We can do much better. We still have to help them as much as we can to be able to.
Anyway, it's a beautiful pattern.
All right. Just a couple more quick examples just to illustrate a couple different things. Here's a question by Jordan and Zsolt. So this example is just to illustrate that this method has absolutely nothing to do with graphs. I am a graph theorist, so most conjectures I know happen to be about graphs, but this method can really be used for any problem that can be described as a finite sequence of finite decisions. So here's a question. How large can the permanence of a 0-1 matrix be if it doesn't contain a 3-1-2 pattern of ones? So here I'm using black squares to denote ones and white squares to denote zeros. And the kind of configuration we are not allowed to have is 3 black squares or ones in this kind of particular configuration. The question is, how large can the permanence of such a matrix be? And Brady and Zsolt had a guess. They guessed that the best thing you can do is the most obvious construction. Take the 3 main diagonals in the leftmost column. You can check that this doesn't contain this 3-1-2 pattern. And you can believe me that if you calculate the permanent of this, you get a nice recursion, and it turns out to be some kind of Fibonacci number -1. All right. Now the question is, how do we attack this using reinforcement? Well, in order to phrase it as a game and really do the same thing as before, we can just go over each entry of the matrix and decide whether we put a 1 or a 0 there. So instead of deciding for edges, take, not take, we just decide do I put a 1 or a 0 for each entry of the matrix. But the reward function is not so obvious anymore. The reward function should be something about the permanence of the resulting matrix, but we also have to take into account that we're not allowed to have any of these 3-1-2 patterns. So we had to somehow combine these two things. And now there are a couple different ways we can do that. Every time I ask people, they say one of two different answers. To me, the most natural choice of reward function to be the permanent of the resulting matrix minus some kind of penalty for every single copy of this 3-1-2 configuration that you contain. You can do it differently. You could also give minus infinity rewards if you do contain one of these forbidden 3-1-2s. That's also a valid way to do it. To me, this is a bit more natural. If you do it this way, you have to be careful that the penalty function is really big enough, because otherwise you might run into this problem that the program realizes that it's beneficial to include some of these forbidden things, because the gain you get in the permanent outweighs the loss that you get through the penalty function, and then you end up solving a completely different problem. You don't want that. As long as the penalty function is really big enough, this method works. And it turns out the best constructions look really quite different from what was conjectured in the previous slide. So these turn out to be the best constructions. They're probably optimal. Of course, I don't have any proof of that. And the really interesting thing is that if you look at the numbers, it starts with 1, 2, 4, 8, 16, 32, 64, and these power sub 2's break down at n equals 8, where the answer is indeed 120. And for n equals 8, I did manage to write down a really ugly computer plus case analysis proof, but turns out 120 is indeed optimal for n equals 8. So the pattern of 2's just bizarrely breaks down at this point. I have no idea what the reason for that is. All right, let me just show you 2 more examples. This is going to be illustrating.
Is the conjecture? I'm confused.
Yeah.
Refuted?
Yeah.
So in hindsight, it was a stupid conjecture.
Well, it was already false for n equals 4, 5, so
so maybe this could have been done by complete brute force. There are not that
absolutely.
many, right? Yeah.
Absolutely. Just to only refute the conjecture, you could have just done brute force, because n equals 8 is already a counterexample. Yeah. But to keep going further, it does get difficult with brute force.
They were victims of the law of small numbers.
Yeah.
But that's a very nice example. Thank you.
Exactly. It's funny, like when I went through arXiv and I just tried every single conjecture I could, there's so many conjectures in arXiv that are false for n equals 3 already. So it's a very strange experience to me to discover this. But it was still a very interesting problem, so it's interesting to keep pushing as far as we can with this method. All right, let's just have one more example, or maybe 2 more examples. This is an example where it's not obvious how to construct a reward function.
Adam, sorry, can you put the slide back?
Yeah.
So this sequence, is it on OAS? 1, 2, 4, 8, 16, 32, 64, 120?
Yeah, after I published this paper, someone else put this sequence on OAS. Yeah.
Okay, that's nice.
Yeah. Okay. So moving on. This next example is going to illustrate sometimes the reward function is not so obvious to choose, and it's also going to illustrate a type of problem for which I don't think this method is a good choice. In fact, the more complicated the conjecture gets, many times it turns out that this method doesn't seem to perform very well. Here's a question. Do there exist 2 graphs? We are going to try to show that there exist 2 graphs so that they have the same distant Laplacian spectrum, whatever that means. First one has some rare regularity property, and the other one doesn't have this rare, complicated regularity property. So without getting too much into what these words mean, let's just imagine roughly what the reward function could possibly look like for a question like this. Well, to me, the most obvious choice would be, imagine you constructed 2 graphs, then the reward function that evaluates how close we are to being a counterexample would consist of 3 parts. First one would have to measure how close are these spectra to each other. Second one would have to measure how close is G to having this very rare transmission regularity property. And the third one would have to be some kind of penalty function if H happens to have this regularity property. So some kind of reward function like this seems to be the most obvious, most natural to me. What I've learned from experience is that if your reward function has 3 or more completely different components that each try to teach the network something completely different, then you're going to really struggle to make this method work. So in this case, that's exactly what happens. Whenever possible, you should try to come up with a reward function that isn't like this. So ideally, we would love to remove one of these three components. For example, it would be lovely if you could figure out how to generate two graphs with the same spectrum directly. I don't know how to do that. Or it would be lovely if you could generate a graph with this regularity property directly. Once again, I don't know how to do that. So this is an example where we have three components in the reward function, and that's a signal that the approach is not going to work very well. And indeed, I managed to make this work here, but in retrospect, probably some much simpler methods would have been much better for this particular problem. It ended up working out, but I don't think it was the best method to use. Turns out two such graphs exist. They have the same characteristic polynomial for the distance Laplacian. I put it here. So the answer is yes to the question. But in general, for such problems, I would not advise to use this method. And just to have one more example, which is instructive to me, is how can we attack infinite problems about what happens when n goes to infinity? Because many conjectures that are the most interesting are of this form. So let's look at this conjecture of Erdős from 1962 that says, take a graph, count the number of four tuples of vertices so that they're all connected to each other, count the number of four tuples of vertices so that no two of them are connected to each other, add up these two numbers. Conjecture is that this sum is minimized by random graphs where you flip a coin for each edge independently, and the conjecture is only about what happens asymptotically and goes to infinity. So this was a famous conjecture. It was refuted by Thomasson after 27 years in a beautiful paper that completely refutes this conjecture. Turns out it's very, very, very false. We wanted to refute this again by using this reinforcement learning method, and together with Gwen Jouret, who is a brilliant computer science professor in Belgium, managed to find a way to do that. So in general, how could you attack such asymptotic or infinite problems where n goes to infinity using this method? Well, there's a simple way and there's a harder way. Simple way is what I usually like to do is take one large value of n equals 50, find the best construction you can, and hope that that construction gives you enough insight so that at that point you can take over and as a mathematician by pen and paper, just finish the job. Unfortunately, for this particular conjecture, it turns out the best constructions are some strange algebraic constructions, and these are just awfully difficult to generalize. So we found some pretty good constructions for a bunch of different large values of n, and we had no idea how to generalize it, fortunately. If this doesn't work, you're left with finding some tricky way to reduce it to a finite conjecture that's potentially stronger, or in this case, I guess, weaker. And one way you can do it in graph theory is called blowing up a graph, which means instead of constructing infinite sequence of graphs, I'm just going to construct one particular graph, take the direct product of this graph with a complete graph on n vertices, let n go to infinity, hope that this sequence of graphs will be a counterexample to the conjecture. The reason to get this is good is because the reward function, which is just number of k4s and number of k4s in the complement of this limit object can be calculated only from properties of G. So you can use simply this limit object here as your reward function, plug it into the right value of n, and if you've done everything right, then this is going to produce a counterexample. Okay, to me, this particular example illustrates two things. First, it illustrates the power of the method, namely that if Erdős had made this conjecture today, it definitely wouldn't have been open for 27 years. With this method, and also with other methods probably, we could have found a counterexample much quicker. On the other hand, it also illustrates one big drawback of this method. Namely, in the previous examples, I always showed you what counterexample looked like. Here, if I show you the counterexample, it's just a graph like that, and I have no idea what this graph is. This just happens to be the smallest counterexample we were able to find. So one big drawback of this method is that even if you succeed, many times you really just get this one bit of information that the conjecture is false. But there's really no question in my head that if you compare it with Thomasson's paper, that paper has just much, much more value than one single computer-generated counterexample. If you read this paper, you understand why the conjecture is false. If you look at this example, you will just know the fact that the conjecture is false, but nothing more. And let's actually talk more about the pros and the cons of this method. To me, the big pro is that it's a really fun method to try. You can really just throw it at any conjecture, and it's really enjoyable to watch this neural network get better and better and better at constructing good constructions. And occasionally, like in the 5 examples I showed you here, it works really beautifully. However, the con is that I showed you 5 examples where it worked beautifully. I didn't show you 90 examples where it didn't work very well. So unfortunately, learning is very, very slow. It doesn't scale very well. And many times, for some reason, if you try this method, it doesn't even perform better than much simpler greedy methods. There are some examples where it does, some examples where it performs amazingly, but most of the time, it just doesn't really do any better than other much simpler methods. Many times I've heard people say that take your conjecture, throw the most sophisticated reinforcement learning out, like Google's AlphaZero, just throw it at it and it will solve it. That is absolutely not the case. Reinforcement learning is not magic, and just because you can attack something with reinforcement learning doesn't mean that you should. So these are some pros and cons of this method. And just a warning, don't expect miracles from reinforcement learning. Sometimes it works very well, but many times it doesn't. And now I'm going to move on to a completely different topic, but maybe it's a good time for a question or two, if there's anything. If not, I will just keep talking and you can ask me all the questions at the very end.
Were you able to modify this to generate conjectures rather than to...
Yeah, so the problem there is how do you quantify which conjecture is interesting? It's very easy to generate 1 million conjectures. I have no idea how to tell automatically which conjecture is interesting and which one isn't. That's very tricky, and I don't know how to do it. Some other people have worked very hard, like there was a software called Graffiti, which was very interesting. It's a bit old now, but I'm sure there is other approaches recently. But the hard bit is really, how do you replace this human insight that tells you whether a conjecture is interesting or not?
Thanks.
Okay, so the problem with reinforcement learning is it's a very local approach. You wiggle edges or just wiggle a neural network a little bit and the graph changes a little bit at a time and you see whether the reward function improves or it doesn't. We wanted to find a different method that gets rid of this localness a little bit and a bit more global approach. So we worked on this with Jordan Ellenberg, Marijn Heule, and Geordie Williamson, and this is still a work in progress. I want to tell you what we came up with so far and what we are trying to do right now. So our idea was, let's pick a problem in mathematics where there is some kind of pattern going on. It's clear to us that there's a pattern, but we don't understand it. And let's see if some kind of neural network, in particular, we wanted to use transformers because they're very, very good at understanding various patterns. And let's see if they can understand it better. And let's see if we can use that understanding somehow in our research. So we started with the following question. That's a cornerstone question in additive combinatorics. How many integers can you choose between 1 and n without having 3 numbers that form 3-term arithmetic progression? But this is a very, very famous problem. Tons and tons of papers written on it. And recently there have been some breakthroughs. Currently, the best lower and upper bounds are the ones displayed. Finally, the upper bound is getting closer and closer to the lower bound. It has already the right shape. Difference is only in the exponent of the log term. Okay, so you're getting close to solving this problem. And what do mathematicians do when they're getting very close to solving an incredibly difficult problem? Well, they make it even harder. So that's what Jordan Ellenberg suggested. Let's have a look at two-dimensional variant. A couple of different ways you can generalize this problem to two dimensions. The one we looked at is as follows. A 3 arithmetic progression in 1 dimension is just 3 numbers, so that the distance between the first 2 is equal to the distance between the second 2. So what happens if we forbid this kind of equation in 2 dimensions? How many points can we choose in the n by n grid if we are not allowed to have 3 points that satisfy that the distance, Euclidean distance between the first 2 is equal to the Euclidean distance between the second 2? Okay, so if you think about it, this is essentially saying what's the largest subset of the grid without any isosceles triangles, But just keep in mind that we are also forbidding flat isosceles triangles. So 3 points lie in some kind of line, but they're equidistant from each other. That's also forbidden. Okay, let's call this number f of n, solution to this problem, and let's see what can we say about this function f of n. First, we try to do it with mathematics. Well, a very simple argument in probabilistic combinatorics called the iteration method gives you a bound, lower bound of the form n over root log n. So this is very simple. I just gave it as a homework problem in my class, and nobody did it, but it's very doable, at least. You can improve this if you're a bit more into literature. This root log n is really just an artifact of the proof. You can get rid of it if you do things well. You can use something called a random gradient dependent set process that gives you a lower bound, small constant times n. The constant you get is something terrible, 1 over a billion. All right, and that's the best lower bound we have. What about upper bounds? Well, just from the fact that every line has to be 3AP free, so you cannot contain a 3AP in any horizontal line, it means you can use the result from the one-dimensional problem, and you get a bound like this. So this is the trivial bound, just using the result from the one-dimensional problem. And that's the best we have. Even proving an upper bound from n to the 1.99, we tried very, very hard and couldn't. So there's a huge, huge, huge gap between lower bound and upper bound. It's between linear and almost quadratic, and we couldn't make any progress on this problem by using odd mathematics. Well, if you cannot solve a problem with mathematics, let's try to do the second best thing, and let's try to come up with a good conjecture about the right order of magnitude of this function by doing some searches with computers. And maybe just from looking at the right constructions, we'll get some insight, and that will help us in the proof. Right, for small grids, we can do it by hand. These are the constructions up to n equals 7. It's not clear whether there's any kind of pattern. For larger n's, you have to use computer, and LP solvers are pretty good in this range of n. Turns out for 8 and 9, the best construction is roughly a circle. For 10, you want to do this kind of alien shape. For larger n, LP solver starts breaking down around n equals 15, but it turns out set solvers are very, very good for this problem. And you end up finding these are exactly the best constructions for n equals 16 and for n equals 27. For 16, there are at least these two very different looking constructions. For 27, there's this construction, but there's also a very different looking one on the left here. For 32, that's where the set solver starts breaking down. It finds a construction, but it cannot prove anymore that it's optimal. So we strongly believe that this is the best you can do for n equals 32, but at this point, we do not have any kind of proof of this fact anymore. All right, and we found all these constructions, and we were happy with them. Unfortunately, we had absolutely no idea how to generalize these constructions, and we had no idea what the pattern was.
What about rectangular grids where you have a fixed, finite?
Right, that's also a very good question.
Then you can get some patterns. Can you?
You absolutely do get some patterns, and we tried some experiments of that sort. We were thinking that if we cannot even solve the square, then maybe the rectangle is too hard in general, but maybe just some special kinds of rectangles would have been doable. We didn't really look into that so much, but that's actually a really good question.
If you're doing the square case, what if you try something like the greedy algorithm? How does that do?
Oh, it does very, very poorly. It gets constructions way worse than these ones. I don't know what asymptotics is able to achieve. It cannot beat n over root log n because that algorithm should already be better than the. I'm not sure. No, that's not true. Mm-hmm. I don't know what the greedy algorithm gets. We tried it, and just based on computer searches, it just does much worse than these other methods.
Do you know? I was looking at the one-dimensional case where the greedy algorithm does pretty well.
Yeah?
Yeah. There are two sequences in the OAIS. One is the optimal solution for the one-dimensional case, and one is what the greedy algorithm gives you. And, well...
Yeah? They're close?
Comparable.
Okay, it's very interesting. In this problem, we definitely tried the greedy algorithm for these computer searches, and they didn't really get close. I guess the question is how close is good enough?
Yeah.
I don't know what the asymptotics would be if you use greedy. Okay, what we wanted is understand what this pattern is. We wanted to have a nice proof that this construction, so we wanted to prove that f prime is at least something, because just take this exact construction, take this parabola or something, take the roots of it, and that just works. Unfortunately, we had no idea how to generalize this particular pattern that we see on this picture. And at this point, we said, maybe n is just too small. If only we had the right construction for n equals 64, say, or something like that, then we could see what the pattern is. In retrospect, this was completely naive. We should have realized that there was no chance that we'll ever really understand what this pattern is, but at this point, we were still full of wonder, and we believed that this would be the case. So we decided we wanted to solve the problem for n equals 64. Now, how do you know that you have solved the problem for n equals 64 if you found some kind of good constructions? Well, before we even try 64, let's make a prediction what the right value will be, so that if in our searches we'll find a construction with this value and we are not able to find anything better than that, that's at least an indicator that we managed to hit the optimal construction. How do we predict what the answer should be for 64? Well, let's plot all of our previous constructions. And, well, this sure as heck doesn't look like a quadratic function. Very much looks like the answer to this question is indeed going to be linear. In fact, the slope of this function is 16 over 9. It seems like, just based on this data, that this function is going to be roughly 16 over 9. Of course, it's still very much possible that there are some log terms that this up to n equals 32 we weren't able to pick up, but that's a reasonable guess from what we've seen so far. If this is the case, then we can extrapolate to 64, because for 16 the answer is 28, for 32 the answer is 56, so probably for 64 the answer is going to be 112. And now all we have to do is just find this construction with 112 points on the 64 by 64 grid. Well, we tried very hard. We tried for 3 months. We threw everything we had, LP solvers, set solvers, all kinds of heuristic searches. And the best we could do is find single 108 after 3 months of searching. So here's the 108 we were able to find. And at this point, we had to realize that there's no chance we'll understand what this is. But we still wanted to find the 112 because we already spent so much time on it. It was very addictive and it was hard to stop. So we're thinking, how can you improve this method and how can you find it even better? We tried all standard methods. That's the best we could do. How can we do better than all the standard methods?
Can you explain why that's symmetric about the middle? Is that accidentally or deliberate?
Absolutely. So for many small values of n, we didn't hardcode any symmetries. And it just turned out that optimal solutions were almost always symmetric. So when we searched for 64, I'm pretty sure we were only looking at symmetric constructions, 2-way symmetry, or sometimes 4-way symmetry. And this is the best construction we were able to find. It's not obvious to me why that should be the case at all. So we wanted to boost this search, and we wanted to use some kind of machine learning on it. So here's what we did. Over these 3 months, we saved every single very good construction we found, every single construction between score of 104 and 108. So many of them were symmetric, but on top of the symmetric constructions, we always tried some local searches that didn't use symmetry. So many of these constructions were not symmetric here. But of course, these are not optimal, but they're all pretty good constructions. Then we took this huge database of 1 million such constructions or so, maybe it was 500,000, I don't remember exactly. And we threw a transformer at this database. And we told the transformer, hey, look, here's 1 million or so constructions. There's something in common in all of these. The human eye, they look very, very different. Find the pattern between these million constructions, understand what's going on here, and please give us more constructions like the ones in this dataset that are not in the dataset already. That's what we did. And we are hoping that after you train a transformer on this data set and you ask it to produce new constructions, some of the new constructions will have 109 or 110 so or more points on them. That was our naive hope. Of course, the problem is that if you ask a transformer to imitate the data set, it's going to imitate the data set. So what actually happened is that it just gave us a bunch of constructions with number of points between 104 and 108, but nothing better, because that's exactly the task that we gave it was. So what do you do now? Unfortunately, this method didn't give us any better constructions. But we noticed that something good was happening. Namely, it was giving us new constructions with this many points at a much, much faster rate than we were able to find with our standard methods. So once we produced 1 million good examples and we trained the transformer on this data set, the transformer was able to generate new quality examples at a much faster rate than we were able to do with our standard methods. And the good thing is that if you accept the fact that 108 is not optimal, not the best result you can get, that means that there exists some 109s in your big search space, and the 109s will be surrounded by 108s. So this means if 108 is not optimal, then many of the 108s you find will not even be locally optimal. Let's say 1% of the 108s will not be locally optimal. You can just add a point to them. So this means that all we can do, we can just do the following: ask the transformer to keep giving us new constructions, millions and millions of them, and for each of them, simply just check whether it's locally maximal. Very, very simple algorithm. We tried that, and it immediately jumped up to 110. Within a few hours, I believe, or maybe a day, I don't remember exactly, we had 110, and 1 week later, we had about 100 different examples of 110. And up to date, that's still the best we have. We have 100 different examples with score 110, but we haven't found anything better than that. In particular, we haven't found the elusive 112, which may or may not exist.
But you've lost your symmetry there.
I think this is still symmetric. I'm not completely sure. It definitely wasn't hard-coded anymore.
It's not symmetric around the vertical.
Right. Seems to have at least top-down flip symmetry, so like some kind of symmetry is still there. It's close to symmetric still, very much. Okay. So this worked in this case, and of course it could be just luck. So let's repeat it for some other examples. Let's try 100 by 100. So what we did, we repeated everything, ran a bunch of different local search methods for a couple of weeks. We saved all of our best constructions. We trained the transformer on the top 10% of constructions we found, and we asked it to generate new constructions like this. From each of them, we launched a tiny, tiny local search. The local searches that we did start with got up to 154. Of course, that's very, very far from optimal. We have no chance of solving the 100 case. But once we put a transformer on top of it, it went up to 160. So here was a construction with 154 that we found by standard methods. And once we trained a transformer on the best constructions, and from that, we asked it to generate new constructions and launch small local searches from these constructions, we ended up with this 160. Still very, very far from optimal, but at least this method boosted our results a little bit. So this seems to be a general method, and currently we are trying with a bunch of different problems. It seems like for some problems it works pretty well, and also for some problems it seems like it doesn't work at all. And currently we don't really understand what problems this is good for, what problems it doesn't work very well for. But the general gist seems to be the following: run your favorite local searches, set solvers, what have you, to end up with a big data set of pretty good constructions. Once you have a big enough data set of quality constructions, you can train a transformer on this, and ask it to generate new constructions that are like the ones in the data set. And if everything went well, and sometimes it doesn't go well, but if everything went well, then this transformer is able to give you new constructions that are as good as the ones in the dataset, much faster rate than you're able to find with your standard methods. But of course, a prerequisite for this to work is that first you have to have big database of good constructions. So you need to put in this work with standard methods, find bunch of pretty good constructions, and only then can you use this method, fortunately. Another thing that we are currently experimenting with is iterating this process. So you start with a big database of good constructions, train a transformer on it, ask it to generate good constructions, many of them, 2 million of them, take the best 10% of them, train a transformer on it, and repeat and repeat and repeat. And it seems like the transformer, what it does is give you a distribution on the space of all constructions. And every time you retrain this transformer, this distribution shifts a little bit. And many times it seems to be shifting towards pretty good constructions overall. But we still have to run many experiments to really understand which problems this method is good for. And I'm out of time, so I just want to leave you with a question here. I would love to understand what the optimal construction for, let's say, n equals 10,000 or 1,000,000 would roughly look like. I have no idea what the best construction would look like. This construction you have, this picture here, is very, very far from optimal. It only has 3,000 points, where that could be probably 18,000 if the conjecture is true. I would love to have any kind of heuristic reasoning or ideas that give us some kind of idea what the picture will look like for n equals some huge number. I have absolutely no clue at this point. And to finish up, I just want to say that right now, machine learning is not very useful in mathematics. There are some applications, but it seems that things are changing and more and more applications start popping up. So I just want to say I'm really excited to see all the new ideas you will all come up with in the next few years. And I hope to see you again next year. Thank you.
Thank you for a great talk. We have time for questions. I have a quick question. I think this has great potential also for number theory. Did anybody try or you to apply these techniques to conjectures in number theory? For example, there are fine-time problems or other things.
I certainly haven't. I think none of my co-authors are very much in number theory so much, so that's the only reason we haven't. But if you have a good suggestion, we certainly could try it. We haven't done so just yet, but that's exactly what we're trying right now. Just try a bunch of different examples and just to see what works and what doesn't. So we can definitely use, you mentioned finite equations. Do you have some specific problem in mind that we should try, you think? This could be good.
Possibly, yeah, maybe. Anyway, it's really interesting. Any questions for Adam?
Yes, I have. In your local search, what kind of score functions did you use? I was wondering if your score functions are parameterized based on various features of the graph, you could have, when you went to your second phase where you look for local search, you could actually score how well your score functions are doing by how long they ended up searching and then actually choosing better parameters in your score function. You might actually might even, with enough data, you might, this would probably take a long time, but you could actually do reinforcement learning with this sort of thing.
So you're suggesting let's learn the best.
Yes, let's learn the best local search score function.
Oh, that's a very nice idea. I love it. Absolutely not what we did here. The local searches we did were very, very simple things. We were really just trying to understand whether the transformer helps or whether we are just seeing, ghosts here. So we really try to simplify the local search to be as simple as possible so we can isolate the fact whether the transformer is doing something useful or not.
Sure. I also wanted to know, so you said you used AlphaZero. Is there is it easy to point where there's an implementation that if one of us wanted to actually experiment with this and do experiments?
Yeah, don't use AlphaZero, please.
Don't use AlphaZero. Okay, all right. What would you recommend?
So I mentioned it here. So last year we had a paper where we took this problem in graph theory. How many edges can a graph have if it doesn't have triangles or 4 cycles? It's a famous problem in graph theory. Nobody knows the solution. And it seemed like reinforcement learning is not doing well. So we tried to use AlphaZero at it. Maybe the reinforcement learning software we used was just not good enough. AlphaZero is going to solve everything. On this paper, I worked with a big team of engineers from DeepMind who are super smart. It took us about 6 months to get AlphaZero running. And even though we had some people from the original group as AlphaZero creators on the team. So AlphaZero is a big piece of very complicated software that takes absolutely forever to get running. I'm not sure if there's probably some kind of public implementations. I would really recommend to stick to much simpler algorithms.
Does your paper have which reinforcement learning software you used, or is it?
So in the paper that I'm mentioning on this slide here, we use AlphaZero, but on the previous paper that I spoke in the first half an hour, I used something called a cross-entropy method, and I have an implementation of that on my website and also on my GitHub. But on the website, I wrote up a nice tutorial where I walk you through the code.
Oh, good. Okay.
Solve some simple examples, and there's even some homework problems because I'm planning to do a course eventually on it. You're welcome to solve the homework problems if you're interested. You really don't have to. I try to make the tutorial as engaging as possible. I hope that's helpful.
Okay, thank you.
Have you considered variants of this isosceles triangle problem raised to 3 dimensions?
Very good question. We haven't tried 3 dimensions at all because we said we cannot even solve 2 dimensions. I would really love to try just to see what kind of patterns happen. One variant we did try a little bit is the torus variant. So many times the best constructions are kind of on the border, and that's just an artifact of the fact that we are on the grid and points in the middle are in more isosceles triangles. But if you replace the n by n grid by the torus, then suddenly every point looks like every other point, and you don't have this artificial clustering on the edges. And there are also some kind of patterns happening. But similarly to this problem, I also have no idea what the pattern is and how to generalize it.
Thank you.
Adam, what kind of hardware were you running some of these algorithms on? Was it just local machines like your desktop, or are you actually putting this on some kind of specialized GPU? Maybe you said this and I didn't catch it.
I didn't say that. It's a good question. In the first half of the talk, everything I said can be done on a simple computer. I was running everything in my computer. There was nothing special about it. Then on the second half of the talk, I got a startup grant at my university, so I could manage to buy a better computer. It's still a standard computer. It's just a higher end one, and everything was run on that computer. For the set solvers, for n equals 32, Marijn was using the cluster at Carnegie Mellon to find these constructions. But you can find this construction with probably other methods as well. It's always very helpful to have more computational resources available, not because you cannot do it without it, just simply because everything is so much faster if you have good compute available. And that's the very disappointing fact to me about this kind of research direction. Many times, smart ideas are beaten by stronger computers. That's just very disappointing to me sometimes.
And since this is such a difficult problem, did you try to have the same problem, but where you restrict the sizes of the triangles? For example, size 1, size 2, up to size 5, and then maybe you can get some patterns?
Yeah, I mean, then you can definitely get quadratic size constructions. The constant is still a question. It would be interesting to see what kind of patterns happen there. I didn't consider that at all, but that could be an interesting question as well.
More questions to Adam?
Yeah, Adam, do you have an intuition why AlphaZero doesn't work well for many problems? Because seemingly it should be better, right, than the simple.
Yeah, so it is better. It works in more cases than the much easier methods, but not that much more. There are many problems for which reinforcement learning just doesn't work very well. And there are some intuitions for why this is the case, but I asked 10 people from DeepMind and I got 10 very different answers. So the answer is I simply don't know. That's the realistic answer here.
So one challenge might be to determine a nice reward function, but what are some other challenges?
certainly that could be an issue that we are all using the wrong reward functions. My intuition is that for many problems, reinforcement learning is just not doing well, and we just don't understand why not just yet.
And,
Or at least I don't.
and finally, for the first conjecture you showed with the graphs, does this work for any graph? Because for the empty graph, it doesn't seem
Maybe it has to be connected. And
it's connected. Yeah.
Yeah, you're connected. Yeah.
Any more questions to Adam? Well, thanks so much for a fascinating talk, and thanks so much for coming. The next talk is by Natasha Tersakov in 2 weeks. Thanks so much for coming.
Thanks, guys.
Bye-bye.
Bye.
Bye.